My name is Eshita Chandwani. I am a software engineer in the gRPC Go team.
Hi everyone, I am Pranjali Saxena. I am a software engineer at Google and an org member of gRPC Go team. Today we are going to talk a little bit about serviceless architecture like Cloud Run and go into what features gRPC has added to make sure it's able to communicate and include serverless platforms in the service mesh. So first thing first, let's begin with what serverless platforms are. Now the name serverless is the most misleading term in cloud computing. Let's clear the air right now. There are still servers. We have not figured out a way how to run code on pure magic yet. What serverless actually means is that you, the developer or the operations team, are no longer responsible for managing those servers. What else can serverless platform do? Serverless platforms are designed to scale from 0 instances up to 1000 based purely on demand. You don't configure load balancers, auto scaling policies or auto scaling groups. The platform do it all automatically. When there are no requests, the platform scales down to 0. Also, less time is spent on operations means faster deployment. Now let's look at the powerful example of this model from Google Cloud, that is Google Cloud Run. Google Cloud is Google's managed implementation of open source technology called native. Google Cloud is built on containers. That's why it offers incredible flexibility. You can take virtually any container image that can listen and respond to HTTP requests written in Go, Python, Java and even C++ and deploy it on Cloud Run. This flexibility means Cloud Run, and this serverless container model in general is applicable to a wide range of scenarios. It's not just for small functions anymore. It's a perfect fit for web services, whether you are serving a full website or just the backend logic for REST or GraphQL APIs. It can handle global traffic without manual interventions. It also executes at asynchronous tasks. Think batch data processing, running reports or simple scheduled scripts that execute periodically. And importantly, due to its containerized flexibility, it can handle more complex workloads, such as hosting machine learning models for AI agents or maintaining persistent connections like those using for streaming. Now you know what serverless platforms are, let's move on to cloud service mesh. To make this serverless vision work, we need a brain to coordinate the traffic with, and that brain is cloud service mesh. A service mesh is a dedicated infrastructure layers that handles the service to service communication. Cloud service mesh unifies traffic director and Anthos service mesh, providing a Google managed control plane that scales globally. CSM uses XDS API for dynamic configuration and supports a proxyless mode that is ideal for gRPC on Cloud Run. We have just covered what serverless platforms are and what is Cloud Run. Now let's go through the diagram and understand how XDS control plane actually handle PSM security, that is called PSM security. Whenever client try to connect to a server using the target schema as shown on the slide like payment or service, the control plane sends necessary security details like TLS configuration and root CA, and then you can get the certificate and deployment infrastructure from the root CA. This system allows for dynamic update of certificates, which means services and security change can happen instantly on both the client and the server without needing a restart. This process ensures that all communication within a service mesh is secure.
Now let's move on to the problems that this serverless platforms created for us to make sure that we are able to include them in in our service mesh. Now to go to that, we must address a fact of life that every serverless instance or platforms are always going to have an ingress proxy in front of it. You ask why? Remember the core promise that serverless platforms made to us, which are that it will always scale down to 0 if there are no requests. If it is idle, it is going to scale down to 0. So we will not have persistent and static IP addresses. So we need a component that is always going to be on, and this is the ingress proxy. It will have a persistent IP and it will manage scaling and routing and make sure that the RPCs go to the correct service. So presence of this proxy means that client and server cannot have a direct connection. All the connections will go through this proxy, and this created some problems for us. Three major problems were client authenticating the proxy making sure that RPCs are routed to the correct service, and server authenticating and authorizing the client. So we'll talk about each of these problems one by one and what gRPC has done to solve these and make sure that users have a seamless experience. The first challenge is a fundamental trust gap by the conflicting security requirements. It is a simple mismatch. As we know, Cloud Run proxy is a public endpoint, so it needs to do standard TLS and use public PKI certificates. But in a standard mesh environment, we used to use private root CAs, which will provide certificates for client and servers. We got these root CAs from the XDS control plane in the config, in the CA certificate provider instance. Now, as we discussed, client and server are configured to only trust certificates from this private CA. So when clients in the mesh see a public certificate, they don't recognize it. They see it as a stranger and drop the connection. So what is the solution to it? The solution is to use system root certs as you would normally do in a standard TLS. But why was it difficult to configure? In standard gRPC, you would manually hardcode it and it should work. But the problem came when we want to configure it through XDS config, because XDS config is supposed to be dynamic and provide configuration for multiple services running on different operating systems and different images. So each operating system is going to have a different file path for the system root certs. So we needed a simple flag for it. So what did we do? We changed the XDS protocol to include a new simple Boolean field called system root certs. So whenever the proxy knows that the endpoint is going to be a public facing endpoint or a ingress proxy Cloud Run service, it will set this system root certs to true and send this config to the gRPC client. Then gRPC will check for two flags. One is this newly introduced system root certs and other is the CA certificate provider instance. If the system root certs is true and the CA certificate provider instance is false, it will ignore any previous mesh CA configurations that it might have gotten and use the system's default root trust store to validate the proxy. And the best part is you won't need to change your code to use this. It is already integrated with the XDS credentials. So if your application is already using XDS credentials, the logic is going to be integrated with it. And you can see the system root certs is added to the certificate validation context message.
Now let me continue with the second major problem while integrating CSM with Cloud Run, that is routing traffic to multiple backends through a single shared ingress proxy. All clients must target the same shared ingress proxy in the serverless ingress layer. However, Cloud Run proxy strictly demands physical service name for successful routing. As a result, mesh clients end up sending the logical XDS cluster name that the proxy cannot resolve. The solution to this is secure authority overwriting. The XDS control plane now instructs the client to include the logical authority header with correct physical Cloud Run hostname. This rewrite happens just before the request leaves the client and is strictly gated by an opt-in security flag in Bootstrap configuration. Let's understand the flow of RPC through this diagram. The XDS control plane configures the client and provides the physical Cloud Run hostname. The gRPC client's load balancer checks for auto host rewrite flag. If authorized, the client overwrites the logical authority header with the correct physical Cloud Run hostname, and the reverse proxy receives the corrected authority header and successfully routes the RPC to the specific serverless backend.
Now on to the third problem, authentication. So what happens in a standard mesh is, as we discussed, client and server are going to get their certificates from the same root CA which is sent by the XDS config. So whenever client tries to connect to the server, obviously is going to ask the client to verify itself, and the client will send the certificate. And since the server knows the root CA and the issuance chain, it will be easily able to verify who the client is. But when a proxy comes in between and the client tries to connect to the server is going to say, I cannot look beyond this wall and I don't know who the client is. Neither is the proxy going to be able to verify it, because proxy understands public certificates. So what did we do? We had to use JOT tokens. So basically we had an identity problem, and as we said, the normal TLS that used to work in a standard mesh system doesn't work anymore. So for authentication, Cloud Run requires security tokens like JOT tokens to prove the identity of the caller, and essentially these tokens should also contain the service account and information about the user. Normally you would have to write custom code to fetch the token and attach it to your request to send it to the server, but we wanted gRPC to do it automatically and not put the burden on the developer. Now gRPC automates this process, and whenever the client is trying to connect to a Cloud Run server, it will query a metadata server and fetch a valid token. And crucially, the token should be for a specific audience, something like what is shown on the screen. So and also this is very seamless, because the XDS configuration is going to tell you how and where to get the token from. So once the token is fetched, gRPC is also going to handle the final step, which is the header injection. We will put the token in the authorization bearer header for every RPC. We do this by implementing the GCP auth filter, and GCP auth filter will maintain a map of credentials for different audiences, and it will check the call attributes, get the correct credentials, and make it do its work. So to do this, we implemented a new type of call credentials in gRPC. These credentials will handle everything from secure client handshake to the metadata server, fetching the correct JOT token and attaching it to the request metadata. So, but you would think that this is going to be a very latency made process, because we would need to query the server every time an RPC goes out. But JOT tokens have a specific expiration time. So we use that to our advantage and cache the tokens. And we only query the token when it expires. And again, we use dynamic audience, that is, the token is specified for a single audience so that it cannot be reused, it cannot be misused. And now for the whole flow, XDS control plane will send the auth filter via type URL and the audience that needs to be encoded in the token. gRPC will maintain a list of these filters along with the call credential implementations. Then a per RPC filter will run which will call the call creds code and get the token from the metadata server, pass the audience to the metadata server and get the audience encoded in the token and attach it to the RPC. Then when the target receives the token, it is going to verify it using JSON web key sets, and it will also extract the audience and verify if it's intended for it. So these are the problems that we had and the ways that we solved it. To know more about these features or any other features, please visit our website grpc.io and YouTube channels. Meetups is where you can meet the maintainers in person and join the mailing list for more updates. So thank you.
Thanks everyone.